Hey everybody, I'm Shane Snyder. I'm a software developer here at Argonne National Labs. I've worked here for around 10 years now, working on things like storage system design and implementation, simulation of storage systems, and characterizing I/O workloads. So just general I/O topics. I'm on Rob Ross's research team here, if you're familiar with it. And today I'll be talking just a little bit generally about file systems and sharing and I/O at the ALCF. Specifically for the Polaris system that we'll be using. So just as some background and some motivation on managing scientific data, starting with applications, they're increasingly diverse in terms of their data management needs. So we've kind of moved from where everything's kind of like big checkpoint restart workloads to a lot more diversity in terms of things like machine learning style workloads where you have models and training and stuff like that needs to happen, and so on and so forth. But the key here is that these applications are, they have lots of diverse data management needs, both in terms of volume and in terms of like access patterns. So obviously they're producing more and more data on these large scale HPC systems, but they're also doing it in different ways, and it creates a little bit of a challenge, especially whenever you can, that's compounding the traditional architectural, I guess, I/O bottleneck that we've seen on HPC systems for a long time. So it's definitely a bit of a challenge. Meanwhile, the hardware trends on systems have enabled a lot of new large-scale storage system designs that can promise a lot of productivity to scientists. And so ALCF and other facilities typically stand up vast amounts of storage resources for users to help kind of bridge this gap between what applications need for data management and what the underlying hardware can provide. And like I said, today we'll talk a little bit about the basics of the HPC data management stack, and try and establish a little bit of best practices for how you can use it in the best way. So we'll start kind of close to the hardware with parallel file systems. So parallel file systems have long been offered by HPC facilities as like a general purpose, one size fits all way to store scientific data. So typically users, it's a very familiar pattern, I guess, for users, using files and directories. It's all stuff that we're familiar with, from programming, with various programming backgrounds, basically. But the idea is that parallel file systems can give you a lot more aggregate capacity and performance than something on your local file system. So, as this figure over here shows, there's maybe a bunch of scientific application processes that are issuing different I/O calls to the file system to create new files or read or write data or things like that. And you can see this kind of simple structure over here with a top level PFS directory and then subdirectories there, with the actual files within the lower level directories. And the point with the parallel file system is that the files themselves can be distributed across lots of storage resources. So you can kind of see that visually at the bottom, how the HDF5 file is, for instance, distributed over 4 storage devices, and the images are over 2. But that's kind of one of the big wins for the parallel file system, is kind of presenting this aggregate amount of capacity and performance to users. So yeah, the characteristics that are appealing about parallel file systems, again, is high performance. So there's lots of parallel I/O paths to lots of storage devices, and these all use really high-speed interconnects. So there's just a ton of aggregate performance that's available to applications. Scalability is another big one. So it's, I guess, somewhat related to performance, but it's the ability to kind of scale storage resources to meet new or future application workloads. So scalability is mostly just making sure the storage system can kind of absorb the workloads from these sorts of applications, even as they scale to larger and larger sizes. And that's obviously really important. And lastly, reliability. So storage systems need some sort of, there's thousands and thousands of independent devices in the storage system. You can't just have it keel over when one of them goes away. So the ability to have high availability and reliability in the face of those failures is critical to ensuring productivity. Some popular parallel file systems available on modern HPC systems, probably the two most are Lustre and GPFS. There's other things like BGFS, and if you look at the IO500, there's tons of research grade, I guess you could call them file systems that can get a lot of performance, but the kind of commercial offerings that are really popular in HPC facilities are definitely Lustre and GPFS. So we'll talk a little bit more about Lustre specifically, primarily because it's the preferred scratch file system here at the ALCF. Again, at a lot of other places too, specifically a lot of the DOE HPC facilities. Lustre's design is centered around an object storage service and a metadata storage service. So there's this metadata servers called MDSs that manage sets of metadata targets, or MDTs, and these are just basically storage devices that are dedicated to storing metadata related information. But essentially the metadata service just maintains the file system namespace. So as the file hierarchy I showed on the previous screen was kind of maintaining that as lots of different client processes try to create new files or read or write files and things like that. There's also object storage servers, OSSs, that manage sets of object storage targets called OSTs. And this is what's used specifically for providing the bulk storage for applications. So large amounts of scientific data for the most part. Lustre clients, so the clients are the application processes on the compute nodes more or less, and these coordinate with the metadata service to either set or query file layouts. But then they interact strictly with the storage servers for reading or writing data. So essentially, whenever you create a file or open it, you can get some layout information back from Lustre that tells you all you need to know about where different pieces of data are stored on different servers. And this really helps out Lustre's scalability in that you kind of offload this requirement to the clients themselves for kind of doing this mapping instead of having everyone kind of reach out to metadata servers on every read or write operation. So that's one of the key points of the Lustre design to keep things scalable. Lustre files are broken into stripes, with stripes kind of they're round robin distributed over the available OSTs for the file, so that could be one or more. And this is visually represented over here on the right. So you have a couple of OSSs. Each one is managing two OSTs, and there's an example file at the bottom with 9 stripes. And you can see how those are round robin distributed over the storage targets. And again, this kind of design decision where you split up files into stripe units and then distribute those is really great for, again, achieving really high performance with a system like Lustre. So achieving the best performance with Lustre does require thoughtful stripe settings, which could be surprising to users who maybe just kind of expect things to be automagic for them. So larger files tend to benefit from larger stripe counts, again, because that's just basically allocating more storage resources for them. Something to keep in mind though, the default Lustre stripe settings may not be optimal. In particular on ALCF systems, the default stripe width is 1, which means files are stored on a single OST. That's maybe not ideal for large scale data sets. So you want to open up as many parallel pathways to the data basically to get good performance. So all that to say, the onus is really on users here to understand striping and to make sure that files are configured properly to get good performance on these systems. So there's a tool called LFS that you can use to set stripe information. An example command here, you can set the stripe size, so how big stripes are. That defaults to 1 megabyte on these systems. And then also the count, which is how many targets are it's striped across basically. And so again, that's a default of 1, but you can use this tool to increase that. Just as a quick example, again, you can see in this, I'm just kind of doing mkdir to create a directory, and you can see that based on querying the stripe information with get stripe, that the stripe width or stripe count is 1. Stripe count and stripe width, basically the same thing. And again, that's the default. And these settings are inherited for all files within the directory. So every file you create in this directory will have the same stripe settings, basically. You could use the LFS set stripe command with the count of 4 to bump up the stripe count to 4. And in this case, every file you create in this directory will be striped across 4 different object storage targets. Recent Lustre versions have introduced this new capability called progressive file layouts, or PFL, that you may have heard of, or you probably will hear about more going forward if you're using Lustre systems. And this is basically just a mechanism that allows striping to be a lot more flexible and dynamic in a way. So PFL replaces this static, these files are striped into these, atomic units across these amounts of servers into something that's more dynamic, that it increases the stripe size as you write more and more data to the file. And what this does is it allows you to for smaller files, just allow them to be striped across, one OST. But as you write more and more data to files, this progressive file layout will increasingly up the stripe width so that more and more storage resources are available. So that's the PFL is not enabled by default yet on ALCF systems, as far as I know, or it's not enabled yet on these systems that we're looking at, but it is, again, something to keep in mind going forward. And again, the whole thought process here is that PFL can provide really reasonable performance for default performance, basically, for a variety of different kind of workloads, whereas we saw with the default stripe width of 1 is really not a good default for large scale stuff that you would see in production. All that to say, still, if you know a lot about, or if you're comfortable with I/O or maybe coordinated with facility staff, probably setting stripe settings manually still could beat PFL. But again, it's just a nice feature to have, so users aren't punished for necessarily forgetting about this behavior. ALCF file systems for Polaris specifically will cover what's available for you. There's the Grand and Eagle scratch file systems, which are Lustre based. And these are for temporary storage of really I/O intensive data by your jobs. They both have 100 petabytes aggregate capacity and can do up to 650 gigs transfers. They're both 160 OSTs, so 160 distinct storage targets that you could stripe your data over, and also 40 MDTs. So there's 40 different devices that are managing metadata as well. And so that's true for both Grand and Eagle. I'm not really familiar with this capability, but it seems that Eagle has some sort of connection with Globus file sharing service. So maybe you guys might hear more about that later throughout the day, or someone or the ALCF docs might have more information on that too, if it's something of interest to you. There's also the home file system. So this is where you land whenever you log on to one of these supercomputers. It's also Lustre based, but this is not for storing application data so much as it is for just kind of general purpose storage of other types of data. So source code or binaries and scripts and stuff like that. And this is nice because it's regularly backed up to tape if you make a boo-boo, basically. There's also node local storage available on the compute nodes themselves. So this is temporary storage available to your job. So there's 2 SSDs with the total capacity of around 3 terabytes that you can use for storing data locally. Obviously, being able to store something locally, you won't pay the big performance or the latency penalty necessarily for going out to the network parallel file systems. So it can be useful depending on what it is you're doing there. But with the caveat, obviously, that you'll need to, it's your responsibility to copy that data that's on the compute nodes back out somewhere persistent when your job ends. So the main takeaway here is that there's numerous options available for you, but it's really, again, on you to make sure you're carefully considering what the intended use of the storage system is and how you're using it. This has implications not only for your application performance, but just general system efficiency and also your data integrity. So making sure you're not assuming that your data will be persistent somewhere where it's not. So next, we'll move on to the I/O library, so how you actually interact with storage. So of course, we'll need some sort of interface for interacting with file systems to store our data. And the good news is that most of these big parallel file systems expose POSIX-like interfaces that we're very comfortable with, familiar with in different computing contexts. So POSIX specifically, if you're not familiar with it, it's this portable operating system interface. It's a Unix standard for having portable ways to do I/O and other sorts of system calls and things like that. But the I/O specific calls that POSIX implements is things like open and read and lseek and close and all those sorts of things that we're probably familiar with in different, from our different experiences. So beyond the actual interfaces provided by POSIX, there's also this notion of the semantics that it's guaranteeing. So POSIX tells you like what sorts of things are guaranteed by different operations. A notable one for parallel file systems is this semantic where successful writes to a file must be immediately visible to subsequent reads to that file. That's a very reasonable semantic that you'd expect to have, subsequent readers being able to see what's already been written to a file. But that's really difficult to enforce on parallel file systems. The issue is that these are distributed systems where each client is maybe caching and accessing information locally. So if a client has updated a file and has that information stored in a local cache, then it creates a lot of issues on how to invalidate that from other processes and to ensure that the most up-to-date thing is visible everywhere. So that's definitely a real challenge and a tricky semantic for parallel file systems in the POSIX standard. So all that to say, POSIX wasn't designed or intended to be used in these sorts of contexts, so large-scale parallel accesses of files. The sort of inflexible and strong consistency requirements really tend to lead file systems to either implement elaborate locking or leasing protocols, or to just completely avoid strong consistency entirely. So to kind of avoid these performance or consistency issues, the best practice in the HPC community has pretty much been to avoid concurrent access of overlapping regions of a file. Which is great, but there's also this kind of notion of false sharing. So if the file system's using locking to enforce consistency, it's possible that the lock granularity is a lot bigger than the access granularities, and you essentially get into situations where you're serializing I/O operations that don't necessarily need to be serialized, which is a big, it degrades performance basically. Okay, so MPIO interface tries to address some of these issues by specifically implementing support for parallel I/O. So the idea is that MPI applications can then use MPIO to read or write data using just various parallel I/O strategies. A popular one is everyone writing to a single shared file. That's something that would be particularly kind of cumbersome to code up yourself and POSIX in a lot of cases, and MPIO kind of deals with a lot of the subtleties there for you. So MPI is a pretty attractive environment for providing parallel I/O support. For one, it already has a notion of collective operations where every process is participating in some task that needs to be performed, like reading or writing a file. MPI also has support for data types for describing the layout of your data, both in file and in memory. So it allows you to come up with a much structured, representations of I/O as opposed to just raw bytes that you would get out of a POSIX interface. And there's lots of different capabilities that MPIO basically offers that allows you to come up with flexible and performant I/O strategies. So it has independent operations, which you can oftentimes do without MPIO, but MPIO does have support for them, so it can cover basically everything. And you can see a representation here of what that looks like with every process kind of a free-for-all for accessing the storage system. You can do collective operations where the processes kind of coordinate with each other and come up with much more reasonable access patterns, as you see here, where maybe only 4 total operations are issued to all of the storage devices. They do non-blocking operations too, which are kind of fundamental for coming up with asynchronous approaches to I/O. And MPIO also implements a lot of, just various optimizations that are subtle and maybe not obvious to users. And these can be just very general things, or they can be system specific things. So, Lustre specific optimizations or things like that. An example of a general optimization is over here to the right. This is the two-phase collective IO algorithm. Essentially, it's just an optimization on collective IO that gives you better performance by splitting it up into two phases. So you have three processes with data on three different storage devices, more or less, and we want to end up with all of the same color data blocks on each process, as you can see on the far right upper part. But essentially, the way you can do this to get better performance is to have specific processes read do this phase one IO part. So they'll just read from a single storage device, and then they'll use the high-speed networks on the compute nodes to distribute the data to its final location. So that turns out to, in most cases, be a lot more performant than having everyone kind of just reach out all to all and gather the data they need. And again, that's an example of something you just get for free by using MPIO. And we'll hear more about MPIO from Rob Latham this afternoon in breakout session 1. Next, IO libraries for managing scientific data. So MPIO is it's a step in the right direction, but still application scientists really don't kind of prefer that sort of abstraction level for managing data. So with MPIO, you're still kind of in the situation where you either need to store independent data products and unique files, or come up with your own way of serializing, multiple data products into a single file, which isn't necessarily, again, the abstraction layer that you would prefer at a application level. HDF5 is a popular data management library that you may have heard of that helps with this. So it's a library and file format that specializes in storing large amounts of scientific data, basically. So you can use it to store, big multi-dimensional data sets, attributes associated with those data sets, and all kinds of other different objects, basically. You can kind of think of an HDF5 file more like a container that stores lots of different things. There's interfaces that allow for you to access individual elements of data sets. You can access subarrays of data sets. You can access entire data sets. There's a lot of flexibility in the interfaces for extracting the data that you need. They have support for collective IO using MPIO, as you would hope and expect, and also independent IO if that's useful. And there's also this vol layer, which you maybe have heard about, that allows an abstraction layer for actually storing the underlying file data. Whereas, typically just goes into raw files. There's different things you could do where, you could use asynchronous operations in a vol layer, or you could use log structured storage, or you could even have the vol layer, avoid files entirely and use like an object store or something like that for storing your data. So it just provides a lot more flexibility for how the data is actually stored. And again, there's an example file here just kind of trying to illustrate how a single HDF5 file can contain, multiple data sets and things like that might be related and useful to be, bin together. And we'll hear, again, more on HDF5 this afternoon in breakout session 1 from Rob Latham. So just putting it all together, the parallel file system at the very bottom layer, right above the hardware, maintains the logical file model and provides efficient access to the underlying storage resources. The IO middleware, which is MPIO in this case, organizes and kind of transforms accesses from all the processes into more performant parallel file system workloads. This is particularly true for collective IO cases. And then at the top is the data model library support. This is things like HDF5, ParallelNet, CDF, audios. These are kind of mapping application level abstractions down to the lower layers of the IO stack, basically. I'll talk briefly about emerging storage technologies, so things like DAOs specifically. I know that Kevin covered a little bit of this earlier, so I won't spend a lot of time on it. But again, HPC storage technology has been changing a lot to meet application IO needs and to embrace emerging storage trends. And so ALCF Aurora will feature Intel's Deos storage system, which is a kind of a like first of its kind object-based storage system instead of a file system for large-scale HPC platforms. On the hardware end, it uses storage class memory and SSDs for storing data. So it's got devices underneath it that have really appealing performance characteristics. And as far as interfaces go, there's a few different options. And again, Kevin covered this, so I'll just go through it pretty quickly, but there's this, you can use the native Deos object library, libdeos, to use objects directly. So you're using kind of their native object model to do I/O. It's unlikely that many users will kind of work at this abstraction level. This is probably used more by I/O libraries and middleware and things like that for trying to get the most out of Deos specifically, but it's less likely that you'll use it directly in your applications. There's also the POSIX-like Deos file system called libdfs interface. And this is, again, it's like a POSIX emulation layer, basically. So it's file and directory abstractions built on top of Deos's native object model. And lastly, legacy POSIX support using Fuse. So this doesn't require any app modifications. And this just uses the traditional POSIX calls that these applications are probably already using. And there are different, performance and different, usage trade-offs that you could consider here. Won't go into it too much because, like I said, Kevin covered it pretty well, and you guys don't actually, you won't be using Deos today anyways, but this was just kind of like a heads up for, what's coming on Aurora, more or less. Next, talk briefly about tools for analyzing application behavior. Application level analysis tools are really critical for better understanding what's happening from an I/O perspective in applications and to inform potential tuning decisions. Darshan is a really popular lightweight I/O characterization tool that's commonly deployed at HPC facilities, including systems here at the ALCF. It does transparent, low overhead instrumentation, so you don't need to change your applications at all. It doesn't kind of perturb their performance mostly, and it gives you instrumentation of multiple layers of the HPC I/O stack that we covered. It gives you detailed counters and timers and statistics for every file that's accessed, and stores all that in a condensed log. And then after your application ends, you can use different analysis tools to inspect the data. The Darshan summary report is probably our most useful tool at the moment, and that's presented visually. It's a quick representation on the right, but I'll talk a little bit more about this in the Darshan breakout this afternoon. There are other tools available that might be useful for getting insights into the behavior of application. Drishti and DXT Explorer are Darshan-based tools that can allow you to visualize trace data or can provide kind of actionable tuning decisions back to applications. I don't have a lot of time to dig into these, but just kind of putting them there for posterity. Tau, which maybe you guys have already heard about this week, I think, which is general call profiling and tracing for HPC applications that can be useful. And then Recorder, which is similar to Darshan, but it does full level tracing. So it does tracing across multiple layers of the I/O stack, which can be really useful for digging into some performance issues. Last thing I'll talk about is sharing data with collaborators. Globus is a platform that enables this by allowing you to manage research data and move, share, and archive large amounts of this data across distributed sites. So Globus will manage data transfers between endpoints, monitors performance and errors. It can retry and correct errors where possible, and it'll report status back to users. And Globus is something that you can either use on the command line, or there's really nifty web interface that you can use for it as well. And I'll avoid stealing too much thunder there and let you guys check out the afternoon breakout session related to Globus if you're more interested in learning about this. So as a quick recap, we've covered pretty much all of the software technologies that comprise the HPC I/O stack, which is used to manage scientific data. Parallel file systems offer high performance, scalable storage of files. There's various I/O libraries that have various abstraction layers that are useful. POSIX is the portable performant layer. MPIO is responsible for implementing collective IO and transforming higher level workloads into POSIX workloads that perform well. And then HDF5 is the nice data management interface that applications kind of prefer. There are tools available for better understanding and ideally improving performance. And there's file transfer sharing mechanisms to enable collaboration across different computing sites. Always consider facility documentation and other resources if you have questions about general best practice or how to do various things, and reach out on support channels if you're stuck. And then again, there's a few different breakout sessions this afternoon that are related to IO and file storage and stuff like that that might be of interest. So if you want to learn more, come check out one of these breakout sessions. And I'll wrap it up with that and see if we have time for any questions.
Thank you, Shane. So any questions for Shane?
Hi, thanks for a great talk. Is there a way to load HDF5 file directly into GPU, with multi-thread capability, so that you can load faster and then train right away without having to go through CPU?
To be honest, I'm not really sure about that. I've not really used HDF5 from the GPU context, so I'm not sure if there's kind of mechanisms that allow you to expose the memory or the file basically directly to the GPU device itself.
But in CPU you can do multi-threading, right? And then
yeah. HDF5 for a long time did not support multi-threading. It does now, as far as I know. I'm not sure it's the best implementation of multi-threading from my understanding of it, but it should work. I think that there's this idea it's got a global lock whenever you're doing IO calls and stuff like that, which isn't great, obviously, but it is supported.
Okay. So let's thank Shane again. So as he said, he's going to be in room 1406 if you have more questions.